you got any question on this problem? Can you solve it? So maybe I first explain a little bit about how we construct a histogram, because I find that some students may not be that familiar with a histogram. Now, one very important key feature of a histogram is that we use the area of each rectangular block to represent data. We are not using the height, we use the area. What does it mean? It means you have more data falling in a particular class interval, then the rectangular block will have larger area. We focus on the area. So if we construct a density histogram, then the total area of all these rectangles add together will be equal to 1. So in other words, each of these rectangles, the area of each of these rectangles represents the proportion, or in other words, the relative frequency or percentage, or whatever you like to name it. So the area of this rectangle is equal to the proportion of data falling within this class interval. So always keep in mind that in the histogram, we use area to represent the proportion. Now, since it is a proportion, so it is equal to the frequency. We can represent the frequency. Right? The frequency divided by the sample size, the size of the whole data set. And the area of a rectangle is equal to the width multiplied to the height. And therefore, the height of the rectangle will be equal to the area divided by the width of the rectangle. So that's why we have this formula to determine the density of the histogram. So under a density histogram, the vertical scale is not the frequency. The vertical scale is not the proportion. The vertical scale is the proportion per unit interval, which is obtained according to this formula. Histogram at the height of the rectangular block, the density histogram, the density at the point S is equal to the frequency divided by the sample size and the width of the class interval for the S belonging to that class interval. Okay? So this is the formula for us to compute the density. So in answering this question, it asks us to determine the density histogram at x equal to 20. So we need to locate the point x equal to 20. And 20 is within this class interval from 15 to 25. So the count, the frequency is equal to 142. So the histogram density at 20 will be equal to 142 divided by the sample size, which is 500. And the width of the interval, which is 10. From 15 to 25, the distance, the width is equal to 10. And this will give us the answer. Sorry. So this is the answer to this question. The histogram, the height of the rectangle erected over the interval containing the point 20 is equal to 0.0284. This is how we determine the height of the rectangle. in a density histogram. Okay. At x equal to 80, so we locate x equal to 80, which is this interval. So the histogram, the density histogram at 80 is equal to the count, which is 6, divided by sample size and the width, and we obtain the density as the point 80. Okay. Now, let's move to question part B. Part B says that we define the interval. We consider the histogram based on intervals of width 20. So that means we are combining the intervals together. We are combining these two intervals from 5 to 25 because we are talking about we defining the interval with width 20. And we combine this together, these two together, this. So we group the intervals together so that the count, of course, will be also grouped together. Okay, and now we calculate the data, the histogram, density histogram as point 20 at the point 80, according to we define the interval. So imagine that we define the interval and then construct the histogram again, and we determine the height of the rectangle at the point 20 and 80. So in part B, histogram at 20. Now this time, 20 belongs to the interval from 25 to 45 because we grouped the intervals together. From 25 to 45, the count this time will be equal to, from 5 to 25, 20 belongs to 5 to 25. So the count becomes 83 add to 142. This will become the count of the interval that contains 20 after we group the intervals together. Divided by the sample size. Now this time the width of the interval becomes 20 because we group them, so the length of the interval will become larger. And this will become 0.0225. And similarly, histogram 80, which is in the group from 65 to 85. So the count will be 13 add to 6. Sample size, width, and it is equal to 0.0019. So you can compare the result of this part B to part A. You see that the number will not differ too much. This number, of course, because we defined the interval. So this number are not exactly the same as the previous two numbers in part A. But they will not be very different. So that imagine that if you construct a histogram, one student construct a histogram using the interval defined in part A, another one construct a histogram with the interval defined in part B. The shape of the histogram will be still preserved. Okay? So this is the idea why we use area to represent the proportion or the count. So it makes sure that even if we define the interval, we define the class interval, the shape of the histogram, the data distribution will be still preserved. It won't be distorted. Is there any question? So this is the key idea about constructing the histogram. Now, let's move on to a more difficult problem. Question number 4. Also related to histogram. And this question is a bit difficult, so maybe you can just work on part 1. Part 1 asks us to show that if we use the density histogram to compute the expected value, it will be given by this formula. Try to think about how we can prove this using the formula of the density histogram. This is a little bit more difficult, but it was a past exam question, so I also like you to know how to solve it. between a subinterval ak to ak plus 1. And within different, just like in the previous question, in different interval there will be a difference in k. There will be different fields. So you may need to partition the interval according to this subinterval. Okay, actually I've given you a hint here. Now, the trick of this question is to partition the integral into the sum of these integrals. The reason is that the density histogram will take different values within different intervals. Just like in previous question, you see, within different interval, we have a different VK. So that a histogram of S will be different within different intervals. So we need to partition the whole integral range into sub-intervals, like this. Integrating the expression from A1 to AK plus 1, we can do it separately, integrating from A1 to A2, and then integral from A2 to A3, and so on. So we can write this integral. Now notice that this is capital K. So this is just the property of integration. And for simplicity, we may write this in terms of the summation notation. Now notice that this subscript is small k. Now, we know how to do this integration. The reason is that this is just bk. This is the class interval, the k class interval bk, from ak to ak plus 1. So we know that within this range, the histogram value will be equal to the formula. Vk divided by sample size and the width of the interval. Now once you can write down this expression, what you need to do is just to do it step by step to do the integration. Now this one, this time this does not involve s. So it can be taken out of the integral sign, and what remains will be just integral of s ds. And I suppose all of you know how to do this integration. To integrate s, it will become s squared over 2. And we evaluate it from ak to ak plus 1. So this quantity will be equal to putting ak plus 1 into this, ak into this, take the difference. So this is the mean, the population mean if we use this density histogram as a probability density function. Now this is still not in the form of the expression that we are asked to prove. So we need to further simplify it so that it will be the form of the expression we are asked to prove. And the rest will be algebraic operation. Notice then that the difference between two squares can be factorized into ak plus 1, ak add together, ak plus 1 minus ak. This is an identity. The difference between two squares can be expressed as the product of the sum and their difference. Now, what is the difference between AK and AK plus 1? This difference is the width of BK, is the width of the class interval. So it is equal to H. So we can see the numerator, there's an H. The denominator, there's another H. These two will be cancelled each other. So what remains will be 1 over 2n sum VK multiplied to AK plus 1. So this completes the proof. Okay. Any question? Now, I know that this may be a little bit difficult for you. In fact, there are some more parts in this question, part 2, part 3, and part 4, and they are challenging questions. And I'm not going to go through here, because I have some other questions I would like to demonstrate to you. But you may try to attempt those challenging questions if you like. And if you encounter any problem, you can ask me. Now, is there any question for this? Now we still have a little time. Let's move on to question number 5, which is related to quantiles. Try to do the calculation. Now this question is just about calculation, not theory. Some computation. But I would also like you to understand how to compute a quantile. So I have a few minutes left. Maybe I will say a few words about how we compute the quantile or the 5 number summaries. Now, first of all, about the quantile, we have a so-called P quantile. Now, P quantile is a cutoff in the data. It tells us that what will be the value in the data in such a way that a certain proportion of the data will fall below this quantity. So we have a cutoff. We would like to know about the cutoff so that we can compare a particular number to this cutoff. So we know whether we are in the top 20% or in the top 5%, something like that. So it is computed according to an index. We first, according to this course, because there are a lot of different formulas to compute quantile, and they make difference. They will be at least slightly different. But according to the formula taught in this course, we compute an index using the sample size add to 1 multiplied to the p. P is the quantile, the proportion we require to determine this quantile. After we compute this one, this may be an integer, it may not be an integer. So we take the integer part. So this is the index. For example, if you compute this index equal to 4.5, then we don't have a number ranked 4.5 in the data set, but you know that it should be somewhere between the 4th number and the 5th number. So we use interpolation. So we take the integer part of this index, and we take the S of R. This is the orderless statistic. That means this is the R prime smallest number. Add to the fractional part, multiply the difference from the next number. So this is how we compute the quantile. To put this in practice, we may use this as an example. Now, first of all, for the 5 number summary, start from the minimum. Minimum in the data is the smallest number in the data set, which is 31. Next will be the 0.25 quantile. How can we compute the 0.25 quantile in this data? We first compute the index using the sample size and this 0.25 as our p. So corresponding to 0.25 quantile, which is also called the lower quartile, the index is computed as 4.75. So that means this number will be the number between the 4th and the 5th smallest number in the data set. So we take the integer part, so it will be equal to the 4th smallest number. Add to 0.75 multiply to the difference between the numbers with rank 5 and the number with rank 4. Okay. So this is the formula for us to compute a particular quantile. So we may refer to the data set, and we simply, because the data set has been sorted, so we can easily locate the number with rank 4 and number with rank 5, which are 69 and 70. 69 add to 0.75 multiply to 70 minus 69. So this is how we compute a particular quantile. And in the 5 number summary, the second number is the 0.25 quantile. And the next one is the median. The median is also the same as 0.5 quantile. And we all know that if we want to compute the median, it depends on the sample size. If the sample size is odd, and then the median will be just the number at the middle range. If the sample size is even, if a sample size is an even number, just like in this case, we have 18 numbers, so the sample size is an even number, then the median will be the average of the 2 middle numbers. So it will be equal to the average of these 2 numbers. Okay? This is the number at rank 9, and this is the number at rank 10. And next will be the upper quartile, which is also the 0.75 quantile. Now, I'm not going to go through the details. You just simply use the similar procedure to compute the quantile. You will find that it is equal to 80 something. $87.25. And finally, we have the last 5-number summary, which is the maximum. The largest number in the dataset is 94. So the 5-number summary are these 5 numbers: 31, 69.75, 78, 87.25, and 94. We call this 5-number summary. Now, why are we so interested in this 5 number? Because this 5 number provides us a partition of the dataset into 4 equal parts. You know, according to the definition of the quantile, this is the smallest number in the dataset, the lower boundary. This number is supposed to be a number in such a way that 25% of the data fall below it. So we know that if you are given this 5-number summary without referring to the dataset, we have some idea on, we have 1/4 of the data fall within this range. And 78 is the median, so we have 50% of the data fall below it. So in other words, there will also another 25% of data within this range. So this will provide some cut-off in the data set, partitioning the data into 4 equal parts. So that's the idea of calculating the 5-number summary. And if we want to put this into a graphical display, that will become a box plot. So box plot is just a graphical display of this 5-number summary. But before we construct the box plot, first of all, we need to determine the outliers. So how to determine the outliers? To determine the outliers, we first compute the interquartile range. Interquartile range is just the difference between this number and this number. The interquartile range is the difference between the lower quartile to the upper quartile. So we take the upper quartile, we obtain the interquartile range. And then we make use of this interquartile range to determine 2 thresholds. And any number beyond this threshold will be regarded as outlier. For example, we'll determine a lower boundary of the threshold, which is equal to 1.5 interquartile range below the lower quartile.